Hello, everyone. My name is Hannah Schunker. I'm a lecturer at the University of Newcastle in Australia. My research interests are focused on understanding the dynamo of the sun and sun-like stars. My research is focused on trying to understand the dynamo by looking at active regions on the sun, trying to understand their subsurface structure and their formation mechanisms, as well as looking to other sun-like stars to understand the interior rotation profile, to understand what drives the solar dynamo.
So in an effort to better understand the interior differential rotation of sun-like stars and to better constrain the dynamo, it's useful to look at a many number of stars. We can do this using astroseismology, which is a tool we have to probe the interior dynamics and structure of the stars. So these modes of oscillations, which I'm showing two examples of here in the movies you see, are stochastically excited by turbulent convection. And these oscillation modes can be represented by their harmonic degree L, their azimuthal order M, and their radial order N. And these will come up again in this talk. So these oscillations are sensitive to the interior structure and dynamics of the stars. What gives us the depth information is modes of different radial order. So modes with different N will have different sensitivities as a function of depth. So by looking at perturbations to the oscillation modes with different radial orders, we can build up a radial profile of the different structure or dynamics of the star. And today we are lucky enough to have observations that are of a similar high quality for a star. For example, what I'm showing here, 16 Sig A, that is 96 light years away, compared to the sun, which is much closer. And so what you're looking at here is a power spectrum from a light curve, from treating the sun as a star in the bottom panel and from 16 Sig A. And you can see and identify the individual modes very clearly and the quality of the observations is clear. Now, the radial order roughly increases with frequency. So higher frequencies are more sensitive to the surface of a star and lower frequencies are more sensitive to the core of the star. And so we can use these modes to look at characteristics of the stars, such as we can measure their radius, we can look at the average density, we can even infer their age, and most importantly for us is to look at the rotation. So if we just zoom in here on a typical section of the power spectrum here, what you're seeing is what we're calling a mode set. The power spectrum in this case is the purple line. The fit to that power spectrum is shown as the red line. And what is fit here is also what we call a rotational splitting. And this is shown by the dashed curve. So with the L equals 1, we have the M equals 1 component. And this is demonstrated more as the broadening of the line there. But if we look at the L equals 2 mode, we can see a distinct splitting. So this rotational splitting is brought about by the azimuthal components moving towards and away from us as the star rotates. But it's difficult to measure this as a function of radial order. What I'm showing on the right here is this rotational splitting measured for different mode sets. So the mode set you just saw is shown in red. And then for higher frequencies are to the right and lower frequencies are to the left. So we're roughly getting a representation of radial order here, but there's not really a strong difference. So this poses a problem. And to be able to really constrain this, we need to reduce this, the noise estimates on our rotation measurements. To infer the rotation from this splitting, we compute an inverse problem. So very broadly, we take our observations and we can match these to a model of rotation that we know something about the physics. And this can be written like this. So we have the observed splittings, which is equal to an integral from the center to the surface of the star over the kernels. So we get these kernels from stellar models as a function of density and rotation and density and pressure and so on. And of course, the rotation as a function of radius, which is what we want to constrain, as well as the uncertainties. And these uncertainties are what we really want to reduce. We can do this in a few different ways. One is by using all the information we have about rotation. So astroseismology isn't the only way to measure the rotation of a star. One way is to use star spots. On the right here, you see a movie of the sun where we see the star spots rotating across the disk at the rotation rate of the sun. In the bottom, what we're seeing is a simulation of a larger star spot on a distant star that significantly reduces the flux emitted by the star and what we can observe. So we see a darkening as this large star spot crosses the disk in our line of sight. So by measuring the rotation with an independent method, we can constrain the astroseismic fits. So when we're fitting the power spectra, we can specify what we think the rotation is already. And we can also use it to constrain the inversions. So the first way, by fitting the power spectra, we can bring this uncertainty down. And in the second way, we can place a constraint on this rotation rate at the surface. Another way we can improve this is to assume an average differential rotation profile. So we don't have the detail we have in the sun for the stars at this point. So looking at the rotation rate that has been inferred for the sun, which we see on the right here, we have the faster rotation at the equator, slower rotation at the poles. You will also notice that below the convection zone, the sun basically rotates as a solid body. Above that, in the convection zone, there is differential rotation. If we take the average of this, we would get something like a step function, where we have solid body rotation in the center. At the base of the convection zone, there is a shear and it changes. So one thing we can do is we can force a function on this parameter that we're inverting, and this would help as well. The second thing we could do here is to add, for example, the spot rotation rate. And so this would constrain the rotation rate near the surface. So this is another option. We explored this in a paper where we modeled the possibilities of inverting for this step, essentially. So we explored constraining the gradient of rotation within sun-like stars. This is what we're interested in, the gradient for for understanding the solar dynamo. But we also explored not just doing this for individual stars, which we talked about, but for an ensemble of stars. So now, with the advantage of observing many stars, is that we can use all of this information to better constrain what we know about certain types of stars, so ensembles. So in our inversion equation, what we can put there is not just one star, but we can analyze the frequency splittings of many stars. And what we will get out of this is an average radial rotation profile. We did an experiment where we estimated the uncertainties we could get by observing a number of stars with Plato, for example, and we divided these into ensembles based on their stellar type, just as a test. On the left, where I'm showing the solar rotation, we see that the solar rotation varies by about 100 nanohertz. This is the gradient. And so if you look at the table on the right, what I've circled there are the uncertainties that we can reduce what we can reduce the gradient to using a number of stars with Plato. And so you can see that the uncertainties are on the order or smaller than the gradient we observe in the sun. So the sun is a moderate rotator and it has a moderate differential rotation. So we can really push it down to sun-like stars. So this is quite a promising avenue. So with ensemble astroseismology, we study stars in groups with common properties. Before I chose stellar type, but this could be anything: mass, temperature, rotation rate. And with that, we can identify trends. So we can identify trends in the astroseismic parameters with the fundamental characteristics, for example. And this is typically what ensemble astroseismology has involved so far. But we want to move to the next kind of level here. So one way is to understand variations in other parameters by holding one parameter fixed. So this is a way to do that experiment. And we can look at it independent of the ensemble property, whatever that is we choose. Another way is to better constrain measurements of individual members of an ensemble. If you have a star that you don't know the rotation of very well, you can't measure it, but it belongs to a well-defined ensemble, you can make some pretty safe assumptions about it, which will lead to understanding the star better. So what I've talked about is looking at the rotational splitting, which tells you about the interior rotation. In addition to using star spot rotation, so independent measurements of rotation that we have and know, and in addition to fitting a function. And we could also put these two together. And these are going to lead to more precise constraints on the rotational splitting and the other astroseismic parameters when we do our fits. But it's not just rotation. What we call the large separation, which is the frequency separation between modes of the same spherical harmonic degree, tell us about the average density of the star. But we could improve this by using stellar radii measurements from the Gaia spacecraft, for example. And this will lead to more precise constraints on the large frequency separation and other astroseismic parameters in our fits. And lastly, the small separation could tell us something about the age. Well, it does tell us something about the age, but we can improve this by combining this with isochrone fits for the stellar model of that star. This will again lead to more precise constraints on delta, the small separation when we're measuring that in the star, and of course, better constraints on the age. So with Plato, we are going to observe absolutely thousands of stars over most of the night sky. The signal to noise is what we want to improve. And this depends on the brightness of the star, the stellar properties itself, so how strongly oscillations are in that star, and of course, the length of the observations. The better noise properties we have if we observe the star for a longer period. So there are going to be a couple of long observation fields in Plato of the length of 2 to 3 years. And these will observe a number of solar type stars with a cadence necessary or sufficient for us to do astroseismology with. And this leads us to doing this next generation ensemble astroseismology, where we just have so many stars and we can go beyond looking at trends. But we need to do this. We need to define useful ensembles based on the physical characteristics of the stars. And we need to couple this with the stars that will be observed by Plato. So looking at the Plato input catalog and seeing how many stars we have there in these useful ensembles. Again, we need to cross-check with other catalogs. For example, Gaia, if we want to know the radius of particular stars. And again, we need to understand the noise estimates from the Plato instrument itself. And in this way, we can put all of this together and compute ensemble uncertainties that we expect for these parameters that we've defined. So this could lead to some really sensitive astroseismic measurements and the most precise stellar parameters that have been retrieved so far, potentially leading to breakthrough advances, not just in stellar dynamo theory, but stellar evolution and galactic archaeology. The skills required for this is most definitely programming skills and knowledge of statistical methods. These are essential. But you don't necessarily have to have experience in data analysis. If you're a theorist or you compute numerical simulations, this is an opportunity for you to gain a deeper understanding of state-of-the-art observational data. So if you're interested in this project, please contact me and we can talk more about it. My email address is there at the bottom. Thanks.